Welcome to The Explainer. Today we're talking about a bug that for a long time was basically hiding in plain sight. We're doing a deep dive into Staphylococcus caprae. So here's our game plan. We'll start with how this bug was finally unmasked. Then we'll head into the lab to see how we ID it. From there, we'll cover the clinical syndromes it causes, get into the nitty-gritty of treatment, and wrap it all up with infection control. This quote just nails it, doesn't it? Staphylococcus caprae isn't some new superbug that appeared out of nowhere. No, it was with us all along. We just couldn't see it clearly. The real game changer was the widespread adoption of technologies like MALDI-TOF, which finally gave us the tools to reliably put a name to the face, so to speak, in our day-to-day work. Now, everything we're about to cover is pulled from a comprehensive Gemini deep search of the current literature. If you're the kind of person who likes to get into the weeds and check the primary data, we've got you covered. The full list of sources is in the accompanying notebook document. Okay, so if better diagnostics were the key, let's step into the lab. How do we actually nail down an identification of Staphylococcus caprae, and why was it so tricky for so long? All right, so you get this on a plate. At first glance, it screams staph. You've got your classic gram-positive cocci in clusters, it's catalase positive, all the usual suspects. But there are a couple of subtle clues right away. The colonies are usually non-pigmented and non-hemolytic, which helps you start thinking it's probably not your typical Staphylococcus aureus. But here's where we really start to separate it from the pack. The biochemical profile is key. Specifically, that combination of being DNase positive but ornithine negative. For years, this is where the confusion happened. It could easily be misidentified as another coag-negative staph, which meant we were completely underestimating its role in serious infections. Today, of course, we have a much better toolbox. For our routine work, MALDI-TOF is the workhorse. It's fast, it's accurate, and it's the reason we're even having this conversation. But, for those really tricky isolates or for research, we still have the gold standard, 16S rRNA sequencing. It's slower, it's pricier, but it gives you the definitive answer. So now that we can confidently ID it in the lab, what kind of trouble is Staphylococcus caprae actually causing out there in the clinic? Well, it turns out it has a particular specialty. And that specialty, its absolute superpower, is forming biofilms. You have to understand this to understand the bug. It creates this slimy protective shield that lets it stick to things like prosthetic joints or heart valves. This shield not only hides it from the patient's immune cells, but also makes it incredibly difficult for antibiotics to get in and do their job. And because it's so good at making biofilms, its clinical calling card is infections related to medical hardware. We see it all the time in prosthetic joint infections and infective endocarditis, especially on prosthetic valves. It's a huge problem for our colleagues in orthopedics and cardiology. As if being a biofilm expert wasn't enough, it's also great at acquiring resistance. And it uses the classic playbook. It acquires the SCC-MEC cassette, which carries the MEC-A gene. That gene produces an altered penicillin-binding protein, PBP2A. And this new PBP2A simply doesn't bind to beta-lactam antibiotics, rendering a whole class of our go-to drugs totally useless against it. Okay, so how do we actually fight this thing? It's tough, it's resistant, and it hides in biofilms. Let's look at the treatment guidelines. Since there aren't specific ones for Staphylococcus caprae, we're basically extrapolating from what we know about other coag-negative staph infections. When you look at the Dutch SWAB guidelines, one thing really jumps out: their heavy reliance on rifampicin for any infection involving a prosthetic device. And the reason is simple. Rifampicin is one of our best agents for penetrating those nasty biofilms.
And you can see that strategy playing out right here. For prosthetic joint and valve infections, the formula is clear. You have your backbone agent, flucloxacillin if it's susceptible, vancomycin if it's resistant, and you always add rifampicin to the mix to tackle that biofilm. Now, if we broaden our view to the international guidelines, like those from the IDSA and AHA, the core principles are very much the same. Everyone agrees biofilms are the enemy. But you'll see some different drug choices and a few other little nuances. So here you'll see agents like nafcillin or oxacillin mentioned for susceptible strains, and daptomycin as a solid alternative to vancomycin. And check out the regimen for prosthetic valve endocarditis, the classic triple therapy, adding in gentamicin for the first couple of weeks. It really underscores just how aggressively you have to go after these infections. Of course, treating kids is a whole different world. The principles don't change, but the execution has to be flawless. Dosing is strictly based on weight, and you have to be on the lookout for different presentations, like late-onset neonatal sepsis, which is a huge concern in the NICU. Here's a quick look at the pediatric toolbox. And one thing that's absolutely critical here is therapeutic drug monitoring. For a drug like vancomycin, you can't just guess. You have to monitor levels to make sure you're hitting that sweet spot between being effective and being safe for these little patients.
All right, we've covered ID and treatment, but you know what's way better than treating a tough infection? Preventing it from ever happening in the first place. So what's the magic bullet for preventing Staphylococcus caprae infections? Well, spoiler alert, there isn't one. It all comes down to the fundamentals of infection control that we already know. It means flawless hand hygiene, using contact precautions for resistant isolates, and being absolutely meticulous about how we insert and manage indwelling devices. So that's the story of Staphylococcus caprae, a pathogen that's really stepped out of the shadows. As I mentioned, all the sources are in that notebook document if you want to dig deeper. We genuinely love to hear from you in the comments. What are your experiences with this organism? And of course, please subscribe for more deep dives like this one. And I'll leave you with this final thought. The story of Staphylococcus caprae is really a story about how better technology reveals threats that were there all along. So the big question is, what's next? Which organism is waiting in the wings to be unmasked